In today's video, we'll walk step by step through this groundbreaking process using the protein structure 6 and 40, a potential therapeutic target. If you are into computational biology, bioinformatics, or simply curious about how science can help treat diseases, stick around. Let's dive into the 4 main stages of this exciting project: protein preparation, ligand preparation, docking, and result analysis. So let's get started. First up, protein preparation. At the heart of every docking simulation is the target protein. In our case, the 6 and 40 protein. But why is protein preparation so critical? When working with protein structures from databases like the Protein Data Bank, they are often incomplete or even messy in their raw state. Water molecules may be cluttering the binding site, missing hydrogens can create inaccuracies, and improper bond orders can affect our results. That's where specialized software comes in. So using Maestro, we begin by adding missing hydrogen atoms to achieve the correct molecular geometry, optimizing the protein structure to correct bond lengths, angles, and sterics, assigning partial charges to mimic how the protein interacts in physiological condition. So first, let's prepare our protein for analysis. We'll use the protein prep wizard. First, we will add our protein structure which we got from the PDB database and looked at in Discovery Studio. Then we will click run and the wizard will create a brand new refined structure for us to work with. Select the pre-processed structure. Next, we will review and modify the structure, deleting any molecules that are far away from our pocket of interest. Then we will refine the structure by adding hydrogen bonds and optimizing them. Take a look. You will see the hydrogen bonds appear. After that, we will remove any water molecules and finally minimize the structure to get it ready for the next steps. Now that we have prepared our protein, let's create a receptor grid. Go to Task and select Receptor Grid Generation. Choose the minimized molecule we prepared earlier. Give your job a name that makes sense for your molecule. Next, go to the Site section. Here, you have 3 options to define the binding site. Manually select the ligand from the protein or enter the XYZ coordinates of the binding site. To do this, go back to Discovery Studio, select your ligand and copy the X, Y, and Z attributes. Then paste them into the corresponding spaces. Now delete the ligand manually from the hierarchy table. Once you have chosen your method, click Run to generate the receptor grid. The grid box specifies the potential binding site, essentially forming a boundary for our search. We ensure it covers all functionally relevant parts of our protein. This process ensures the 6 and 40 protein is fully simulation ready and able to provide accurate predictions during docking. Remember, the cleaner our protein structure, the closer we get to identifying small molecules that could treat diseases like iron-deficiency anemia. Moving on, we need to prepare potential ligands, the small molecular superheroes responsible for binding to the 6 and 40 protein. But what exactly makes a good ligand? To prepare our library of ligands, we begin by designing small molecules that might bind to 6 and 40. So first of all, we carefully draw the 2D chemical structures of our ligand candidates. These are typically small molecules with functional groups tailored to bind to specific sites on the target protein. Next, we hop back into Discovery Studio where our 2D sketches transform into realistic 3D structures. By optimizing the geometry and assigning charges, these ligands are made ready for simulation. Finally, these molecules are collected into a virtual library. By working with a diverse set of ligands, we increase our chances of finding high affinity binders for 6 and 40. That's why building a diverse and structurally relevant library is a critical step. Now that we have our ligand sets ready, let's embark on the exciting journey of ligand preparation using Maestro. If you are new to this, don't worry. We will take it one step at a time and stick with the auto settings for now. First, upload the ligand set file you carefully prepared in Discovery Studio. This is where the magic begins. Next, head to the job settings and feel free to turbocharge the process by increasing the processors if needed. Then click the run button and watch as the job submits. It's like sending a spacecraft into orbit. Keep a close eye on it as it turns green when it begins, signaling that the preparation process is underway. Monitor the job's progress and make sure the error count remains at a reassuring 0. With Maestro guiding us, we will be navigating the world of ligand preparation like cross in no time. And there we have it. We have successfully generated 38 ligand outputs from our initial set of 6. But what's fascinating is that these outputs differ in their protonation states and isomeric points. These means we now have a diverse set of ligand variations to explore, each with its unique characteristics. Now comes the exciting part, docking. This step is where we use computational power to simulate how our ligands interact with the protein. Using Maestro, a powerful docking software, here is how it works. Let's start the docking process. Go to Task and select Protein Ligand Docking. A new interface will pop up where you will upload your prepared protein file. Remember to select the zip file. Next, choose your ligand file. Now, let's move on to the setting. As a beginner, select Standard Precision for a good balance between speed and accuracy. Choose Flexible for ligand sampling to allow for more conformational flexibility. Make sure to check the epic state box. Under Output, select Pose Viewer and choose the number of poses you want to generate per ligand. I recommend 5. Also check the box for pre-residue interaction codes. Finally, click Run to start the docking process. Once everything is set, the virtual magic happens. Ligands from our library are positioned, rotated, and scored based on how well they fit into the binding site. This simulation mimics the way real molecules interact within the human body. Docking simulations give us a ranked list of ligands. The candidates with the highest binding affinity take the top spots. The results are in, but the work isn't finished yet. Finally, let's analyze those results and uncover which ligands could hold the key to treating iron deficiency anemia. For each ligand, we evaluate binding energies. The lower the energy, the stronger the interaction. Now that we have our docking results, let's analyze them. As we can see, our molecule NS6 has the lowest energy, indicating a strong binding affinity. To get a better look, let's select both the molecule and the protein, then left click to merge them. This will give us a clearer visualization of how NS6 interacts with the protein, allowing us to gain deeper insights into their binding mechanism. Do the ligands form hydrogen bonds, hydrophobic interactions, or salt bridges with the binding site? At the end of analysis, we are left with a list of promising candidates ready for experimental validation. While docking is just the first step, it provides a highly efficient roadmap for developing treatments for iron deficiency anemia.